So welcome to the sixth session of Marami, session about mobility. So I'm going to introduce Hocine Cherifi, which presents a work about topological analysis of temporal contact networks based on human mobility models.
Okay, so it's a very long title. So this is a work that I've done with colleagues from Senegal. So Jibril is the student, Sherif is his advisor, and Moussa is the professor who is. So what are we trying to do? We want to do a lot of things, but first of all, what we want to see is to look at similarities between temporal contact networks and artificial temporal contact network or proximity network based on mobility model. After that, we want to use that on epidemic spreading and stuff like that. But first of all, why do we want to do that? Because there is really few contact networks. It's very time-consuming, and it's very difficult to have such data, and usually the data sets are very small. It's very difficult to have them. So if we can generate artificial contact networks who have the same properties, topological properties, than the real data sets, we will have win something. And then we will, if we understand the mobility models and the impact of the parameters of the mobility models on the temporal network, we may infer some relation between topology and mobility and use them on epidemic spreading. So that is the idea. So there is one data set which is really well known about real data set. It's called sociopattern. It has been done by people from Easy Foundation in Torino. And what's his name, the French guy, Alain Barra in Marseille. They are the two guys who did the social pattern. So you see the data set is a small data set. It's in a school, 232 children, 10 teachers, and it has been done in Lyon. And the temporality, it's 2 days. So they have a contact network. And they say that 2 individuals in these contact networks are in contact if they are face-to-face during 20 seconds. So if you go on the website of sociopattern, you can have a movie of the evolution of the contact network. So those are the classes. And in the middle, you have the teachers. And you have the relation between that and the evolution of the relation, 10 classes, and the evolution during the time. This must be les récréations. I don't know what you call that, when everybody's all together. So you see, and you see that these networks are very difficult. For example, this network is very difficult to exploit it because it's a very small network, few connections. So statistically, it's not very interesting. So this network is called the primary school. There's also another network that has been done by the same people. So it's always Alain Barra who did that, but now he moved to high school. And so high school student people in France know what are the classes préparatoires. People are more in high school, but they are like people in primary school. I'm joking, mais c'est pas grave. So it was in Marseille, and it was during 5 days, and same type of data, same model. So here I have a representation by classes, and you see that there is much more connection than on the primary school. So now, let's look at this, I would say, the properties of those data. First of all, we are giving the density of contact during the time. So you see that human beings have I would say, deterministic behavior. They sleep during the night, and they don't see people at school during weekends. So you have dentists during the day, and this evolved. You have that from day to day. So I would say this is the deterministic behavior, and in the data that we analyzed, we should, when people do economics, the first thing that they get rid of is the trend. And we didn't do that. But we should, I think, get rid of all the deterministic behavior, because what we are interested in is the statistical part of the network. So we have that. So you can see that it's periodic, and contacts are very regular. So after that, there is the famous law of, I would say, network science, the power law. Wherever you go, you find the power law. So I will, rather than speaking about the power law, I prefer to speak about heavy-tailed degree distribution, that which says that I would say that lots of people have few things, and few people have a lot of things. So it's inhomogeneous. So what we are looking, it's the contact duration at high school, day by day, every day. And you see this is in log-log. So when you plot the distribution in log-log, if it's linear, it's a power law, and you can estimate the coefficient of the power law. So you see that this is a good fit, and this is also a good fit for the... So it means that, in fact, there's most of the contacts are very small, have a low duration, and there is few contacts who have a very long duration. So this is a trend that we find in real data, heavy tail distribution. The intercontact duration, so it's between two contacts. It's exactly the same type of flow. That's why I say we have always this. We can observe exactly the same behavior day by day and aggregated on the whole week. Another property that you can find on contact networks or proximity networks, it's the burstiness. So something is bursty when it arrives, an event is bursty when it arrives. There's a lot of events in a short time and then a long time without event. So this is something that we find in contact. So there is moments where there's a lot of contacts between people and then long moments without contact. So to compute, in fact, to quantify this property, people are using two coefficients, which are linked to the mean and the standard deviation of the intercontact duration. So Burstiness coefficient and local variation. So we said that a phenomenon is bursty if this coefficient is positive, and if it is bursty if this one is between those two values. So let's look at burstiness for high school. Here you have the burstiness coefficient. So it's bursty if we are here, and it's also if the local variation is in this quadrant, I would say. Je ne sais pas comment on dit. So to summarize, what I can say, it's real contact networks have at least this property. They are regular and there is, I would say, things which are periodic and deterministic. Those networks have a heavy tail distribution of contact duration, heavy tail distribution of intercontact duration, heavy tail distribution of contact pairs, and and they are bursty. So now we know a little bit about the topological property of these temporal networks. Let's look at the mobility model. So we use 4 mobility models. Those mobility models are not really human mobility models, but mobility models which are used on Wi-Fi contacts. So I go from the simplest to the more sophisticated. So random waypoint, Gauss-Markov model, truncated Levi-Talk, and steps. Let's go for step. So random waypoint, it's very simple. So you go from point to point. How do you go from one point to the other? So first, you choose a destination. You go at position XE with a uniform distribution between a mean value and a max value. After that, you also choose a speed in a uniform distribution between Vmin and Vmax. And then when you arrive at distribution, you have a post time. And the post time is between Tmin and Tmax. And this is so all uniform distribution. And this is the kind of trajectories that you can have with this model. So it's a little bit erratic, I would say. So to have something smoother, you need to have something a little bit more sophisticated. So no, the Gauss-Markov model, it's the same type of thing. You find the position xi and yi, depending of the speed and orientation. And you need something which is a little bit random in this. You need to put some randomness. How do you add randomness? So I would say this is something that you will tune your speed, but you put a Gaussian distribution in here. You put a Gaussian distribution in here, a random variable which has a Gaussian distribution. And you put the randomness, and this allows you to change the direction and stuff like that. C'est tout? So this is the Gauss-Markov model. The truncated Levi-Talk, it's a little bit more sophisticated, but in this case, we enter the power laws rather than Gaussian. So you have this. And then steps, you have the algorithm. So how do we do now that we have our mobility model to generate a contact network? So we put some nodes, we put some nodes in a square, and after that, we let them move, and if a distance is less than a certain distance, we will put a link between the nodes. So now let's look at the properties of these mobility models. So if we look at the density of contact, we don't have this, we cannot observe the same thing that real, the periodicity of real contact. We cannot do that. We cannot observe that. It's something which is random. And so it's a purely random situation, I would say. If we look at the distribution, you have all the mobility models. And here you have primary school and high school. So I let you judge which is the most near. I would say that for me, this one is a good fit for this property. Same thing for contact duration. You see that the one which is more, well, a good fit must be this one. Intercontact duration, we have primary, so Gauss-Markov is a good fit. And burstiness, so high school, primary school are very bursty, but the other ones, maybe this one, steps is very interesting for burstiness. So what can we say? This is a table which summarizes all the properties, the best fit of the distribution. So to summarize, what can we say? We can say that there is no mobility model who can, at the moment, help us to generate artificial temporal networks. So what do we plan to do? First of all, there is two ways. The first way is to say, yes, we will try to improve, put more parameters in the mobility model. But this is complicated. So the first thing that we will do, I think, is just to change, to mix the mobility model. Say, right now, we have compared mobility models. Now we say, if we put two type of population or three type of population which are different, maybe we will get something better. So this is the first step, and this is the next thing. But we have done already something with this. We have used those mobility models on epidemic spreading, but and I think that we are in a good, comment on dit? Direction, I hope. Voilà, merci. Thank you. Bon, question.
Questions?
Allez, il est où, mon ami?
So you think that combining the existing synthetic models, you can you would arrive to simulate, but then I mean you will always need to compare it to other environments, because then we saw primary school, high school. Yes. But I guess that if you take other situations, I don't know, people in a museum or everything else, so it will be completely different.
Alors, we are waiting for a data set. There's Sune Lehman, it's very difficult to build this data set. So we are in contact with Sune Lehman, who is building a data set, because you really need people, put them, comment on dit, des sensors. So it's, so there's a guy who is building this type of data sets, and we will have this type of data set. But in fact, we think that the models are not good enough. So there's two ways. Either we use more parameters, you know, that you will tune, or maybe we can use the simplest ways to check if just mixing the population will give us something which is better. We are not sure. It's very empirical. It's just a feeling, that's all, not... but it's another way. Voilà. Voilà. It's just another way to add more parameters without doing anything. Oui.
Do you have any interpretation on why the real data is different from the random model?
First of all, humans are very predictable. They are not random at all. Human beings, they are very predictable compared to... so we can put some randomness in humans, but not so much. So I think the first thing that we have to do, as I said, is to get rid of all which is not random. Because the only thing that we can deal with is randomness. We are doing statistics. We want randomness. If we don't have randomness, it's... but right now, I think that we need first to have data, and there's very few data. And so it's very important if we can generate, even if we have data, you see the size of the data sets is 300 nodes. Don't do statistics on 300 nodes. You know, it's not... so we really need to generate this type of data. And even if they are not, if they are a little bit far from real situation, they may help us. So that's why we are really trying to work on that.
Other questions?
Okay.
Other questions? Okay.
Just a question about the application. So for this number of nodes, can we imagine to monitor, to measure for a longer period, and then to cluster the people?
Yes, I think so. But I think that the guy, if they could... where is Christophe? Christophe is, I think that's his student who will do the next presentation. It's easy, you can think of doing that, but after that, human beings don't want you to do that. You know, they want where the sensor for 2 weeks. They accept to wear a sensor for 2 days or 3 days. So yes, that would be marvelous. More people, I'm thinking in the IUT to build, you know, Christophe has done some sensors everywhere, and he gave to the students, you know, cell phone, and he can follow the student. But the sensors are expensive. They don't work and stuff like that. So it's not so easy to build such. You need money to do that, I think, to do bigger data sets. So that's why people are doing. When they did that, it was, I would say, socio-pattern. It was a big project, really a big project.
So, another question? Okay. So, thank you again.
OK, thank you. Ah, c'est Arslan. So, voilà.